there's a planet out there, so far away that sunlight takes over 4 hours just to reach it. 4.5 billion kilometers from Earth's soil. Out past Jupiter's storms. Beyond Saturn's rings. Further than Uranus. Sitting at the edge where sunlight dared to reach there. Introducing the richest planet in the universe. Neptune. And for decades, we thought we understood it from textbooks. We knew it as the another ice giant. Cold, distant, unremarkable, except for its blue color. Then Voyager 2 showed up in 1989. What the probe found didn't make sense. This discovery goosebumps the world, receiving almost no energy from the Sun. Was burning hot from the inside. Storms raged across its surface at supersonic speeds. A magnetic field twisted in ways that violated our models. And orbiting backwards around the planet was Triton. A moon that had no business being there. Neptune wasn't dead. It was one of the most violent, energetic places in the solar system. Today, we're revealing apart everything strange about Neptune. And there's a lot. If you're here for actual science, not the usual Neptune is blue and far away stuff you get everywhere else, subscribe now. We're going deep, and if this is your thing, you don't want to miss what's coming next. Let's start with the problem that's bothered planetary scientists for 35 years. Neptune receives virtually no energy from the Sun. At 30 astronomical units out, the Sun looks like a slightly brighter star. The light that reaches Neptune is so weak that if you stood on its surface, hypothetically, you'd experience perpetual twilight. Not darkness, but not day either. By every calculation, Neptune should be frozen solid. An inert ball of ice and rock, slowly cooling over billions of years, until it reaches equilibrium with the surrounding space. Instead, Neptune pumps out 2.6 times more heat than it absorbs. That's not a small discrepancy. That's a planet generating its own weather system from internal energy alone. And nobody knows exactly how. Here's what makes it stranger. Uranus. Uranus is Neptune's twin. Similar mass, similar size, similar composition, mostly water, methane, ammonia ice. And Uranus sits closer to the Sun, meaning it receives more solar energy than Neptune does. But Uranus is colder, significantly colder. It radiates almost nothing from its interior. So what's Neptune doing that Uranus isn't? The first explanation scientists proposed was leftover heat from formation. When planets form, gravity pulls material inward. That compression generates enormous heat. Same reason a bike pump gets warm when you use it. All that kinetic energy converts to thermal energy. For the first few 100 million years after formation, planets are scorching hot. Then they cool, slowly radiating energy into space until they reach equilibrium. But here's the problem. Neptune and Uranus formed at the same time, from the same material, in the same region of the early solar system. If primordial heat were the answer, both planets should be radiating similar amounts of energy. But they're not. Neptune is an outlier. So either Neptune retained more heat, meaning something about its internal structure insulates better, or there's another energy source we haven't identified. The second hypothesis is ongoing differentiation. Inside Neptune, heavier elements are still sinking toward the core. As they fall through the mantle, pulled by gravity, they release potential energy as heat. Think of it like a ball rolling downhill. Gravity does work on the ball, and that work converts to kinetic energy. Inside Neptune, dense materials settling inward release energy continuously. This process could sustain Neptune's internal heat for billions of years. And if Uranus experienced some catastrophic impact early in its history, something that disrupted its internal structure, it might have lost the conditions necessary for ongoing differentiation. There's evidence for this. Uranus has an extreme axial tilt, 98 degrees. It essentially rolls on its side as it orbits the Sun. That tilt likely came from a massive collision early in its history, possibly with an Earth-sized object. If that impact scrambled Uranus's interior, it could explain why differentiation stopped, why the heat stopped. But for Neptune, the process continues. Regardless of the source, Neptune's internal heat drives convection. Hot material rises from deep in the mantle. Cool material sinks. This creates massive circulation currents, like a pot of boiling water but on a planetary scale. And those convection currents don't stay buried. They reach the atmosphere. When hot plumes of material rise into the lower atmosphere, they transfer energy. That energy drives winds, generates storms, creates the supersonic jet streams that make Neptune the windiest place in the solar system. We'll get to those winds in a moment. But first, we need to understand what's happening inside the planet, because Neptune's interior isn't just hot, it's weird. Not actually icy. Let's clear up a misconception. Neptune is called an ice giant. But there's no ice anywhere near its surface. When astronomers say ice, they mean water, methane, and ammonia in any form, solid, liquid, or gas. It's a compositional term, not a temperature descriptor. And inside Neptune, those ices exist in states that don't occur naturally on Earth. The atmosphere. Neptune's atmosphere is thin compared to the planet's total mass, maybe 10 to 20% of the radius. It's mostly hydrogen and helium, like Jupiter and Saturn. But Neptune has significantly more methane, about 2 to 3% of the atmosphere. That methane is why Neptune looks blue. Sunlight hits the atmosphere. Methane absorbs red wavelengths and reflects blue. The result is that deep azure color we see through telescopes. But methane does something else too. At high altitudes, ultraviolet light breaks methane molecules apart, creating haze, layers that obscure the deeper atmosphere. Those hazes are why we can't see Neptune's interior directly. We're observing cloud tops, not the surface. The atmosphere has distinct layers. The troposphere extends from the cloud tops down to where pressure reaches about 100 bars. This is where weather happens. Clouds form, storms rage, winds howl. The stratosphere sits above, where temperatures actually increase with altitude due to methane absorption of solar UV radiation. This temperature inversion creates stability, preventing vertical mixing. The thermosphere reaches outward towards space, where temperatures climb to several hundred Kelvin despite the planet's distance from the Sun. This heating comes from auroral activity and magnetospheric interactions. Energy dumped into the upper atmosphere by Neptune's chaotic magnetic field. But the real strangeness begins below the atmosphere. The mantle, superionic ice. Below the atmosphere lies the mantle. This is where things get genuinely bizarre. The mantle is a thick shell, maybe 10,000 to 15,000 kilometers deep, of water, methane, and ammonia, but not in any form you'd recognize. At the top of the mantle, temperatures reach around 2000 Kelvin. At the bottom, near the core boundary, they exceed 5000 Kelvin. That's hotter than the surface of the Sun. But here's the twist. Despite the heat, the mantle isn't a normal liquid. Under pressures millions of times greater than Earth's atmosphere, water doesn't behave like water anymore. It becomes superionic ice. In normal ice, water molecules lock together in a crystalline structure. Solid, rigid, familiar. In superionic ice, only the oxygen atoms lock into a solid lattice. The hydrogen atoms break free. They flow through the oxygen lattice like a liquid, carrying electric charge. It's simultaneously solid and liquid, a state of matter that only exists under extreme conditions, conditions that don't naturally occur anywhere on Earth's surface. Scientists only confirmed superionic ice exists in 2019, using diamond anvil cells to compress water to pressures over 2 million atmospheres, while simultaneously heating it with lasers. The result? A crystalline structure with the oxygen atoms frozen in place and hydrogen ions zipping through the lattice like electrons through a wire. And superionic ice conducts electricity. The hydrogen ions moving through the oxygen lattice create electric currents. Those currents generate Neptune's magnetic field, but in a way completely different from Earth's magnetic field. We'll come back to that magnetic mess in a bit. For now, just understand. Neptune's mantle is an electrically conductive shell of exotic matter, thousands of kilometers thick, hotter than the Sun's surface, existing in a state that violates everyday intuition. Diamond rain deep in the mantle, under crushing pressure, something even stranger happens. Methane molecules, CH4, can't stay together. At pressures around 10 million atmospheres and temperatures near 5000 Kelvin, the bonds holding carbon and hydrogen together break apart. Carbon separates from hydrogen, and at those conditions, carbon doesn't remain gaseous. It crystallizes into diamonds. This isn't wild speculation. Scientists at the SLAC National Accelerator Laboratory in California recreated these conditions in 2017. They used the world's most powerful X-ray laser to compress polystyrene, a hydrocarbon similar to methane, to Neptune-like pressures. The result? Nanodiamonds formed within picoseconds. Inside Neptune, those diamonds don't just form, they fall. Diamond is denser than the surrounding superionic fluid, so gravity pulls it downward. Tiny crystals collide, stick together, grow larger. Maybe they reach millimeters, maybe centimeters. Maybe, deep in the mantle where pressures peak, they grow to the size of hailstones, and they rain down toward the core. A constant precipitation of crystallized carbon, falling through an ocean of superionic ice, potentially accumulating at the core mantle boundary in vast diamond deposits. This process, diamond precipitation, might be ongoing right now. It could have been happening for billions of years. And as those diamonds sink, they release gravitational potential energy, converting it to heat. That heat contributes to Neptune's internal energy budget. It drives convection. It powers the storms raging across the surface, all because methane molecules break apart under pressure, and carbon crystallizes into the hardest natural material in the universe. The core. At the center of Neptune lies a core, probably rocky, possibly metallic. We don't know its exact composition. Our models suggest it's about 1.2 times the mass of Earth. Made of silicates and iron-nickel alloys left over from planetary formation. But we've never observed it directly. The core is buried under thousands of kilometers of superionic ice and atmosphere. All we have are indirect measurements, gravity data from Voyager 2, models of planetary formation, comparisons to Uranus. What we do know is that the core is hot, probably around 5,000 to 7,000 Kelvin. Hot enough to keep the mantle fluid, hot enough to drive convection currents that reach the atmosphere. And those convection currents are what make Neptune's atmosphere so violent. Supersonic jet streams. Neptune's equator moves at 2,160 kilometers per hour. That's not the planet's rotation speed. That's the wind speed. To put that in perspective, the fastest tornado ever recorded on Earth reached 486 kilometers per hour. During the 1999 Bridge Creek Moor tornado in Oklahoma. Neptune's average equatorial wind speed is more than 4 times faster than the most violent storm Earth has ever produced. At that velocity, Neptune's winds are supersonic, faster than the speed of sound in its atmosphere, which is around 400–500 meters per second depending on altitude and composition. How is that possible on a planet so far from the Sun? The energy budget. Neptune receives almost no energy from the Sun. At 30 AU, solar heating is negligible, less than 1/900th of what Earth receives. But internal heat is abundant. The planet radiates 2.6 times more energy than it absorbs, and all that excess energy has to go somewhere. It goes into the atmosphere. Hot material rises from the mantle into the lower atmosphere, creating powerful convection currents. Those currents drive winds, not through solar heating like on Earth, but through internal energy release. This makes Neptune fundamentally different from terrestrial planets. On Earth, atmospheric circulation is driven by differential solar heating. The equator heats up more than the poles. Warm air rises at the equator, flows poleward, cools, sinks, and returns. That's the Hadley cell, the basic engine of Earth's weather. Neptune doesn't work that way. Its atmospheric dynamics are powered from below, not above. The energy source is internal, distributed across the entire planet, creating convection everywhere simultaneously. The Coriolis effect. But raw convection doesn't create organized jet streams. For that, you need rotation. Neptune spins once every 16 hours, fast for a planet its size. That rapid rotation deflects moving air through the Coriolis effect, turning vertical convection currents into horizontal wind bands. On Earth, the Coriolis effect creates trade winds, westerlies, and polar jets. Different latitude bands move at different speeds, creating distinct circulation cells. On Neptune, it creates something far more extreme. Because Neptune's internal heat is distributed evenly across the planet, convection occurs everywhere simultaneously. There's no strong equator-to-pole temperature gradient like on Earth. Instead, you get uniform upwelling across the entire atmosphere. That uniform energy input, combined with rapid rotation, generates wind bands that circle the entire planet. Stable, powerful, supersonic. The strongest winds occur at mid-latitudes, around 30 to 50 degrees north and south, where the Coriolis effect is strongest and convection currents are most vigorous. At those latitudes, winds can reach 600 meters per second. That's Mach 1.5 in Neptune's atmosphere. Retrograde winds. Here's the strangest part. Neptune's equatorial winds move backwards. Most planets have prograde equatorial winds, meaning they move in the same direction as the planet's rotation. Earth does this. Jupiter does this. Saturn does this. Neptune doesn't. At the equator, winds blow at 400 meters per second in the opposite direction of rotation. That's called retrograde superrotation. And we don't fully understand it. One hypothesis involves magnetic interactions. Neptune's magnetic field is tilted and offset from the planet's center. More on that shortly. That creates complex electromagnetic forces in the conductive layers of the atmosphere and mantle. If those forces couple with atmospheric flow, they could drive winds in unexpected directions, including retrograde. Another hypothesis involves wave dynamics. Large-scale atmospheric waves, Rossby waves, can transport angular momentum from one latitude to another. If the wave patterns set up correctly, they could drive retrograde flow at the equator while maintaining prograde flow at higher latitudes. But that's still speculative. The truth is, we don't have enough data to say for certain why Neptune's winds behave this way. What we do know is that those winds are stable. Voyager 2 measured them in 1989. Hubble has monitored them for decades. The wind patterns don't change much over time. That stability is remarkable. On Earth, jet streams meander, storm tracks shift, weather patterns evolve seasonally. Neptune's winds don't care about seasons. They blow constantly, driven by internal heat, shaped by rotation, moving faster than sound. The Great Dark Spot. In 1989, Voyager 2 spotted something enormous in Neptune's southern hemisphere. A storm, oval-shaped, the size of Earth. They called it the Great Dark Spot. It looked like Jupiter's Great Red Spot, a high-pressure anticyclone rotating counterclockwise, persisting for... Well, that's where the comparison breaks down. When Hubble looked at Neptune in 1994, the Great Dark Spot was gone, vanished. Jupiter's Great Red Spot has lasted at least 400 years. Neptune's Great Dark Spot lasted less than 5. Why? The answer probably lies in atmospheric instability. Neptune's winds are so strong and convection currents so violent that storms don't last. They form, rage for a few years, then dissipate. Since 1989, Hubble has observed multiple dark spots appear and disappear. 1994, a new dark spot in the northern hemisphere. 2016, another northern spot, tracked for 2 years. 2018, a southern spot, observed drifting toward the equator before fading. All temporary, all unstable. These storms aren't like anything on Earth. They're three-dimensional vortices extending deep into the atmosphere, constantly disrupted by convection from below. Bright methane clouds often accompany dark spots. High-altitude features that form when the vortex pushes methane gas upward into colder regions, where it condenses into ice crystals. Those bright clouds are actually easier to see than the dark spots themselves, which are only visible because they're regions of clearer atmosphere, allowing us to see deeper into the planet. The instability of these storms tells us something important about Neptune's atmosphere. It's in perpetual chaos. There's no stable stratification, no long-lived weather patterns. Just constant turnover driven by energy bubbling up from thousands of kilometers below. A broken dynamo. Most planets generate magnetic fields through a process called the dynamo effect. Earth does it with a molten iron core. Liquid metal flows, driven by convection and planetary rotation. That flow creates electric currents, which generate a magnetic field. The result is a dipole field. 2 poles, north and south, aligned roughly with the planet's rotation axis. Simple, elegant, predictable. Neptune has a magnetic field, but it doesn't look anything like Earth's. When Voyager 2 measured Neptune's field in 1989, Scientists were stunned. The field was tilted 47 degrees relative to the rotation axis, and it wasn't centered. It was offset from the planet's center by more than half a radius, displaced toward the southern hemisphere. That's not a dipole. That's a multipolar mess. The shell dynamo Neptune's magnetic field isn't generated in the core. It's generated in the mantle. Remember supersonic ice? That electrically conductive slush of water, methane, and ammonia occupying the mantle. That's where the magnetic field comes from. Convection currents in the mantle drive fluid motion. That motion generates electric currents in the conductive ice. Those currents create the magnetic field, but because the dynamo operates in a shell rather than a centralized core, the field is distorted. It has multiple poles. The field lines don't run straight. They bend, twist, loop back on themselves. This is called a shell dynamo, and it's fundamentally different from the core dynamos that power Earth's, Jupiter's, and Saturn's magnetic fields. On Earth, the magnetic field originates deep in the core and extends outward relatively smoothly. The poles are near the rotation axis. The field is mostly dipolar, two poles dominating the structure. Neptune's field has multiple poles scattered across the surface. The strongest magnetic pole isn't at the north or south pole of rotation. It's offset, sitting at mid-latitudes. And because the dynamo operates in a shell rather than a point source, the field structure changes depending on where you are relative to the planet. Magnetic chaos. Neptune's multipolar field creates a chaotic magnetosphere. On Earth, the magnetosphere is relatively simple. Solar wind, a stream of charged particles from the Sun, compresses the magnetic field on the day side, stretches it into a long tail on the night side. The field lines guide charged particles toward the poles, creating stable auroral zones. Neptune's magnetosphere doesn't work that way. The offset tilted field means different parts of the magnetosphere rotate in and out of the solar wind as the planet spins. Every 16 hours, one Neptune day, the entire magnetic structure wobbles. Sometimes the strongest pole faces the Sun. Sometimes it faces away. Sometimes it's on the side. This creates pulsating dynamics. The magnetosphere expands and contracts. Magnetic reconnection events happen unpredictably. Charged particles don't follow simple paths. They spiral chaotically through the field, bouncing between magnetic mirror points that shift every few hours. It's a magnetosphere in constant flux. And that creates auroras unlike anything seen on other planets. Say our arcs. Neptune has auroras, but you can't see them with your eyes. They're called stable auroral red arcs, or SAR arcs. They emit faint red light in the infrared spectrum. Wavelengths around 630 nanometers that are barely visible to human eyes, and completely invisible from Earth's surface through atmospheric distortion. The James Webb Space Telescope finally captured them in 2023, the first clear images of Neptune's auroras ever recorded. SAR arcs form when charged particles interact with atmospheric molecules at mid-latitudes, not at the poles like on Earth. Weak solar wind. There's another reason Neptune's auroras are so faint. At 30 AU from the Sun, the solar wind is weak. Solar wind intensity drops with the square of distance. At Earth's orbit, 1 AU, the solar wind delivers about 400 particles per cubic centimeter, traveling at 400 kilometers per second. At Neptune's orbit, that drops to less than 0.5 particles per cubic centimeter. There just aren't enough charged particles reaching Neptune to create powerful auroras like Earth's or Jupiter's. The auroral displays we do see come from a combination of solar wind particles and particles from Neptune's own magnetosphere, ions stripped from the upper atmosphere or from Triton's tenuous nitrogen envelope. These particles get trapped in Neptune's magnetic field, bouncing back and forth between magnetic mirror points. Over time, some spiral down into the atmosphere, colliding with molecules and creating faint red emissions. But the process is inefficient. The auroral power output on Neptune is orders of magnitude weaker than on Earth. Thermospheric heating. Here's something strange. Despite weak auroral activity, Neptune's thermosphere is hot. The thermosphere, the uppermost layer of the atmosphere, reaches temperatures around 500 to 700 Kelvin. That's bizarre. Neptune receives almost no solar energy. The sun's heating at that distance should create thermospheric temperatures around 100 Kelvin. So where's the extra heat coming from? The leading hypothesis: auroral heating. Even though Neptune's auroras are faint, they deposit energy into the upper atmosphere continuously. Over time, that energy accumulates, heating the thermosphere far above what solar radiation alone could achieve. It's similar to what happens on Saturn's moon Triton, where weak auroral processes heat the upper atmosphere, despite Triton being even farther from the Sun. But the exact mechanism is still debated. Some models suggest ion drag, where charged particles in the magnetosphere transfer energy to neutral molecules through collisions. Others point to Joule heating, where electric currents flowing through the ionosphere generate heat like a resistor. We don't have enough data to say for certain. What we do know is that Neptune's thermosphere is hotter than it should be, and that heat has to come from somewhere other than the Sun. Auroral processes, even weak ones, seem to be the best explanation. Retrograde orbit Neptune has 14 known moons. Most are small, irregular chunks of rock and ice, probably captured asteroids and Kuiper Belt objects. But one moon stands out: Triton. Triton is massive, 2,700 kilometers across, larger than Pluto. It accounts for 99.5% of all the mass orbiting Neptune, and it moves backwards. Every other large moon in the solar system orbits in the same direction as its planet's rotation. Jupiter's Galilean moons orbit prograde. Saturn's Titan orbits prograde. Triton orbits retrograde, opposite to Neptune's spin. That's not natural. You can't form a large moon in retrograde orbit through normal planetary accretion. Moons form from the protoplanetary disk, material orbiting the young planet in the same direction it rotates. Retrograde orbits don't happen that way. Something else happened to Triton. Captured from the Kuiper Belt. The leading hypothesis: Triton didn't form around Neptune. It was captured. Triton probably originated in the Kuiper Belt, the region of icy bodies beyond Neptune's orbit, where Pluto, Eris, Makemake, and thousands of smaller objects reside. It might have been part of a binary system, two objects orbiting each other, like Pluto and Charon. Then, one day, billions of years ago, that binary wandered too close to Neptune. Neptune's gravity tore the system apart. One object gained energy and escaped, flung outward into a wider orbit. The other, Triton, lost energy and was captured into a chaotic, highly elliptical orbit around Neptune. Over millions of years, tidal interactions with Neptune circularized that orbit, pulling Triton closer, stabilizing its path. But the retrograde motion remained. Evidence for this hypothesis comes from Triton's composition. Spectroscopic analysis shows it's remarkably similar to Pluto: nitrogen ice, methane, carbon dioxide, water ice. It's chemically more like a Kuiper Belt object than a regular moon, suggesting it formed in the outer solar system rather than in orbit around Neptune. Tidal heating Triton's retrograde orbit creates tidal stress. As Triton orbits, Neptune's gravity pulls unevenly on different parts of the Moon. The near side experiences stronger pull than the far side. That differential force flexes Triton's interior, generating heat through friction. It's the same process that heats Jupiter's moon Io, turning it into the most volcanically active body in the solar system. On Triton, tidal heating keeps the interior warm enough to sustain geological activity, despite being 4.5 billion kilometers from the Sun and receiving virtually no solar energy. The amount of tidal heating depends on Triton's orbital eccentricity and the rigidity of its interior. Right now, Triton's orbit is nearly circular, so tidal heating is relatively weak, probably a few gigawatts of power, comparable to a large volcanic eruption on Earth, but sustained over millions of years. But in the past, when Triton's orbit was more elliptical, tidal heating would have been intense, possibly strong enough to melt the interior, creating a global subsurface ocean. That ocean might still exist today. Cryovolcanism. In 1989, Voyager 2 observed something nobody expected: geysers, erupting from Triton's surface. Not water geysers, not lava. Nitrogen geysers. Triton's surface temperature is around 38 Kelvin, negative 235 degrees Celsius. One of the coldest surfaces in the solar system, cold enough to freeze nitrogen solid. But beneath the surface, conditions are different. Triton's crust is mostly nitrogen ice mixed with methane and carbon dioxide. Beneath that lies a layer of warmer material, possibly water ice, possibly liquid water mixed with ammonia acting as antifreeze, kept warm by tidal heating and radioactive decay in the rocky core. When pressure builds beneath the crust, perhaps from subsurface heating, perhaps from seasonal warming, it fractures the ice. Nitrogen sublimates, goes directly from solid to gas, and erupts in towering plumes reaching 8 kilometers high. Voyager 2 captured images of at least 4 active geysers during its flyby. Dark streaks on the surface, deposits of organic material called tholins, mark where geysers had erupted and deposited debris downwind. These tholins form when methane in Triton's tenuous atmosphere gets hit by ultraviolet light from the Sun, breaking apart and recombining into complex organic molecules. The geysers carry these molecules from the surface into the atmosphere, where winds, yes, Triton has winds, spread them across the Moon. Triton has an axial tilt and experiences seasons, though each season lasts decades, because Neptune's orbital period is 165 Earth years. When the southern hemisphere faces the Sun, even the faint Sun at that distance, it warms slightly, enough to sublimate nitrogen ice, enough to trigger eruptions. When Voyager 2 flew by, it was southern summer on Triton. The geysers might have been active because of that seasonal warming. We don't know if they're still erupting today. Nobody's been back to check. The death spiral. Here's the grim truth about Triton. It's doomed. Because its orbit is retrograde, tidal interactions with Neptune don't boost its orbit. They decay it. Every orbit, Triton loses a tiny bit of energy. The tidal bulge it raises on Neptune drags against its motion rather than with it, sapping orbital momentum. Gradually, over millions of years, Triton is spiraling inward. The calculations are straightforward. In about 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces overcome the Moon's own gravity. When that happens, Triton will be torn apart. Its structure will fracture. Pieces will separate. The Moon will disintegrate into fragments. Those fragments will spread out along Triton's orbit, eventually forming a ring around Neptune. Possibly the most spectacular ring system in the solar system, rivaling Saturn's. But that's billions of years away. For now, Triton remains, a captured moon spewing nitrogen ice into space, slowly falling toward its own destruction. And beneath its frozen surface, there might be an ocean, a hidden sea warmed by tidal flexing, possibly containing organic chemistry, possibly, just possibly, harboring the conditions for life. Faint and forgotten Neptune has rings. Most people don't know that. They're not like Saturn's rings, bright, massive, easily visible from hundreds of millions of kilometers away. Neptune's rings are faint, dark, made mostly of dust and small rocky fragments. Before Voyager 2, their existence was debated. Ground-based observations in the 1980s occasionally detected brief dips in starlight as Neptune passed in front of distant stars, stellar occultations. But the dips were inconsistent. Sometimes they appeared. Sometimes they didn't. Some astronomers thought Neptune had incomplete rings, arcs of material rather than full circles. Voyager 2 settled the debate in 1989. Neptune has 5 main rings. Gala, the innermost ring, about 41,000 km from Neptune's center, faint and diffuse. Leverrier, 53,000 km out. Lassell, a wide, faint ring between Leverrier and Arago. Arago, 57,000 km out. Narrow, under 100 km wide, barely detectable. Adams, the outermost ring, at 63,000 km. Brightest of the rings, containing dense arcs. The Adams ring is the weird one. Ring arcs. Most planetary rings are uniform. Material spreads evenly around the planet over time. Collisions between particles redistribute momentum, and gravitational perturbations from moons smooth out any clumps. Within a few years or decades, you'd expect a ring to reach equilibrium, a continuous band of material with no gaps. But the Adams ring has arcs, dense clumps of material separated by empty gaps. These arcs have names borrowed from the ideals of the French Revolution. Liberté, égalité, fraternité. There's also a fainter arc called Courage. These arcs have persisted for decades. Voyager 2 saw them in 1989. Hubble has monitored them ever since. They're still there. That shouldn't be possible. Ring arcs are dynamically unstable. Collisions between particles should spread material along the orbit within years. Gravitational interactions should smooth out the density variations. But Neptune's arcs remain. Shepherd moons. The answer lies in resonances, orbital patterns where gravitational interactions repeat periodically. A small moon named Galatea, about 175 kilometers across, orbits just inside the Adams ring. Galatea's gravity creates a 42-43 resonance with particles in the Adams ring. For every 42 orbits Galatea completes, particles in the ring complete 43. That resonance traps material in specific locations, preventing it from spreading. Think of it like pushing a child on a swing. Galatea's gravity pushes ring particles at just the right frequency to keep them bunched up in arcs. It's a delicate balance. If Galatea's orbit shifted even slightly, maybe due to interactions with Triton's massive gravity, the resonance would break and the arcs would disperse. And that might already be happening. Recent observations from Hubble and ground-based telescopes show that the arcs are fading. The Courage arc has almost disappeared. Fraternité is dimmer than it was in the 1990s. Nobody knows why. Maybe Galatea's orbit is precessing. Maybe collisions are grinding ring particles into dust that escapes the resonance. Maybe Triton's gravity is slowly destabilizing the system. Neptune's rings might be temporary. They could last another 1,000 years. Or they could vanish in a century. We don't know. Dust and micrometeoroids. Neptune's rings are also dusty, far dustier than Jupiter's or Saturn's rings. That dust comes from micrometeoroid impacts. Small chunks of rock and ice in the rings get hit by tiny particles traveling at high speed. The impacts shatter the ring material, creating clouds of fine dust. That dust doesn't stay in the rings long. Solar radiation pushes on it, radiation pressure, causing the smallest particles to spiral inward toward Neptune. Over time, the rings should erode. Material gets ground into dust. Dust gets pushed out of orbit, and eventually the rings disappear. The fact that Neptune still has rings suggests they're young, maybe only a few 100 million years old. Where did they come from? Probably a shattered moon. One of Neptune's small inner moons, maybe Naiad or Thalassa or Despina, might have been hit by a comet or asteroid, fragmenting into the material we now see as rings. Or maybe the rings are remnants of Triton's capture. When Triton was pulled into retrograde orbit, it might have gravitationally disrupted smaller moons, tearing them apart and scattering debris into ring orbits. We don't know for sure, but the rings exist, and they're another piece of Neptune's dynamic, chaotic history. The unsolved mysteries. Despite everything we've learned, Neptune remains deeply mysterious. We've had one spacecraft visit Neptune, Voyager 2, for a few hours in 1989. Since then, all our data comes from telescopes: Hubble, James Webb. Ground-based observatories with adaptive optics. But telescopes can only tell us so much. Here's what we still don't know. Why is Neptune so hot? We have theories: primordial heat, ongoing differentiation, diamond rain releasing energy. But we don't have definitive answers. We need seismic data. We need to measure heat flow from the interior directly. Why do storms appear and disappear? The great dark spots come and go on timescales of years. What triggers them? Why don't they last like Jupiter's great red spot? Is it atmospheric instability? Convective disruption? We don't know. How does the shell dynamo work in detail? We know superionic ice generates Neptune's magnetic field, but the exact mechanism is unclear. How do convection currents in the mantle couple with rotation to produce such a distorted field? Models exist, but they're not conclusive. What's happening in the deep interior? Is there really diamond rain? How thick is the superionic ice layer? What's the core composition? We need gravity mapping, seismic measurements, data we can't get from telescopes. Why do retrograde winds exist at the equator? The physics of retrograde superrotation is poorly understood. Magnetic coupling? Wave dynamics? Something else? We need atmospheric probes. Direct measurements of wind speed at different altitudes. Does Triton have a subsurface ocean? Tidal heating suggests it might. But we need seismic data or magnetometer readings to confirm. An ocean would make Triton one of the most compelling astrobiology targets in the solar system. Future missions NASA and ESA have proposed missions. Concepts exist. Plans have been drawn up. Neptune Odyssey was one concept, an orbiter designed to study Neptune's atmosphere, magnetosphere, and moons over multiple years. Trident was another, a Triton flyby mission focused on detecting a subsurface ocean and characterizing cryovolcanism, but neither has been funded. The problem is cost. Neptune is far. Even with gravitational assists, it takes 12 and 15 years to reach Neptune with current propulsion technology. A mission launched in 2030 wouldn't arrive until the mid-2040s. Total mission cost, $2 to $3 billion. That's a hard sell when there are cheaper targets, Mars, Europa, Enceladus, that might answer astrobiology questions sooner. But Neptune isn't just about finding life. It's about understanding ice giant physics, a class of planet that's common in the galaxy but poorly understood. Most exoplanets discovered are Neptune-sized or smaller. If we want to understand those distant worlds, we need to understand Neptune first. And a Neptune orbiter could answer fundamental questions about planetary formation, atmospheric dynamics, magnetic field generation, and moon evolution. It would be worth it. Ice giants are everywhere. When we look at exoplanets, planets orbiting other stars, we find that Neptune-like worlds are common. More common than gas giants like Jupiter. More common than rocky planets like Earth. The Kepler Space Telescope and TESS have found thousands of exoplanets in the 1 to 4 Earth radius range, roughly Neptune-sized. We call them sub-Neptunes or mini-Neptunes, and they're the most abundant type of planet in the galaxy. But we don't understand them. Are they scaled-down versions of Neptune? Do they have hydrogen-helium atmospheres, superionic ice mantles, magnetic fields generated by shell dynamos? We don't know, because we've barely studied Neptune. If we want to understand exoplanets, if we want to know which ones might have habitable moons, which ones might retain atmospheres, which ones might generate protective magnetic fields, we need to understand Neptune first. Magnetic fields and habitability. Neptune's magnetic field teaches us something important. Not all magnetic fields are created equal. On Earth, our magnetic field protects the atmosphere from being stripped away by solar wind. Without it, Earth might look like Mars, dry, barren, atmosphere lost to space. But Neptune's magnetic field is chaotic, tilted, offset, multipolar. It doesn't provide stable protection the way Earth's does. Does that matter for habitability? If a Neptune-like exoplanet has a habitable moon, like Triton with its potential subsurface ocean, does the chaotic magnetic field help or hurt? We don't know. But understanding Neptune's magnetosphere could inform models of exomoon habitability. Atmospheric dynamics. Neptune's atmosphere is driven by internal heat, not solar radiation. That makes it a testbed for understanding brown dwarfs, objects between planets and stars that glow from internal heat. Brown dwarfs have atmospheres. They have clouds, storms, wind patterns, but they're too faint and distant to study in detail. Neptune is close enough to observe. Its atmosphere operates on similar principles: internal heating, convective dynamics, magnetic interactions. By studying Neptune, we learn how atmospheres work when solar heating isn't the dominant factor. And that knowledge applies to exoplanets around dim red dwarf stars, where internal planetary heat might rival stellar heating. Neptune is a reminder that we don't fully understand our own solar system, a planet that radiates internal heat for reasons we can't completely explain. Winds that break the sound barrier, driven by energy buried thousands of kilometers deep. A magnetic field generated in a mantle of superionic ice. Matter existing in a state that doesn't occur naturally on Earth. A captured moon moving backwards, spewing geysers of nitrogen ice, spiraling slowly toward its own destruction. Every time we look closer at Neptune, it breaks another rule. And that's what makes it fascinating. Because if a planet in our own neighborhood, one we've known about for almost 200 years, can still surprise us, what does that say about the exoplanets we're discovering? How many ice giants orbit distant stars, hiding diamond rain and superionic mantles and retrograde moons? How many worlds operate on principles we haven't even imagined yet? Neptune isn't just a planet. It's proof that the universe plays by rules we're still learning. And every mystery we uncover is a reminder we're just getting started. The next generation of telescopes, ground-based observatories with massive mirrors, space telescopes with advanced instruments, will reveal more about Neptune's atmosphere, its storms, its magnetic field, maybe we'll send another spacecraft. Maybe in the 2040s, a probe will orbit Neptune, mapping its gravity, measuring its interior, studying Triton up close. Maybe we'll finally answer the questions Voyager 2 left behind. Until then, Neptune remains blue, distant, violent, beautiful, a frozen world that refuses to be dead. Thanks for watching. If this kind of deep dive is your thing, no fluff, just the science nobody talks about, subscribe. We're covering Jupiter's magnetosphere next, and trust me, it's even stranger than Neptune's. Until then, keep looking up.